Wild Health is about optimizing you. We use genomics, blood work, biometrics, microbiome assessment, many other tests, and a conversation with you to come up with a full health optimization plan. What's the perfect diet, exercise, and supplement plan for you and only you? The Wild Health podcast is about optimizing all of us. Here we cover the cutting edge science that gives you the base to be able to apply the personalized plan we give you as a patient. To sign up as a patient, go to wildhealth.com. Or if you're a physician or health coach and you want to learn how to do this for your patients, we're happy to help as well. Wildhealth.com for all the information on becoming a patient or working with us. Hey, Mike, how's it going?
Hey, Matt. Good. First snow here in Oregon, so going well. How about you?
I'm good, other than I'm like literally sweating right now, worrying about the title of this this podcast. Um, we we recently saw an article that Peter Attia put out about biologic aging, and we disagree with some of it. So they were discussing titling this podcast "Why Peter Attia is Wrong About Aging," which is quite the clickbait title. And I hope they don't use that. But if they did, Peter, let me explain. Like, we love you. We agree with like 90% of what you say. I mean, everybody loves Peter. Like Mike, I think you know this, but when Peter talks about longevity and health, Father Time takes notes. And when he talks about metabolism, enzymes stop to listen. So we got mad respect for Peter.
You know, one that I heard that one time he did a blood test and the results came back as the reference standard of pure perfection.
Actually, I know that's not true because he doesn't do blood tests. His cells just whisper their secrets to him.
Did you know that he doesn't age? Time just slows down and sometimes even stops to savor his health advice.
Yeah. Most people actually, there's a lot of misconceptions about him. Like diet, a lot of people think that he was really big into the ketogenic diet and then he stopped like several years ago. But the truth is, he never followed the ketogenic diet. Like all of us, the ketogenic diet tried to follow Peter Attia, but it couldn't keep up. That's what actually happened.
Yeah, I also heard that he's been doing less fasting these days. But again, most people don't know that when he was actually fasting, the calories literally decided to fast in solidarity with him.
No, I actually knew that. Yeah, I heard that too. And a lot of people think he's a big swimmer, but he actually doesn't swim at all. The water actually moves around him as as a sign of respect. Um, the point being, we've got mad respect for Peter Tia, and we totally didn't have ChatGPT come up with those for us. Like we just made those up ourselves. We do happen to disagree with some of the points that he made in this article about biologic aging. And to be fair, though, I think we both would agree that we pretty much 100% agreed with him a couple months ago, but we've changed our minds recently. And we're going to talk about today why we've changed our minds. I do think it's probably important, Mike, just to start.
Yeah, totally. And just like you said, Matt, I really agree with Peter. Up until a couple months ago, due to some new studies coming out, there's not much I have to disagree with until recently. But epigenetic clocks, very simply, are a tool that we can use to estimate somebody's biological age, and we call it an epigenetic clock because we're actually looking at the epigenome, and the epigenome is part of the genome that's not actually coding for proteins. It's the part that gets methylated and allows the DNA to get coiled up and put back inside the nucleus. And where we put these methyl sites, these methyl groups, determines whether genes get transcribed or don't get transcribed. And every cell has its own epigenetic signature. And what we see is that with aging, this epigenetic signature changes. So back in 2013, Peter talks about this, but back in 2013, we saw our first generation epigenetic clocks come out. And what they were doing was just basically training a methylation array. So measuring different methylation sites around like 500 or so, I think, if I remember correctly, or maybe it was even lower than that. It might have been like 200 or something. But in any case, not a ton. But different methylation sites that were they found to be associated with chronological age. So it's important to note that these first generation clocks, and Peter mentions this in his letter, are all trained against somebody's chronological age. So how good is methylation at estimating your chronological age? Not super helpful, right? Because you know how old you are, at least presumably you know how old you actually are. So the accuracy of these methylation clocks was not really that helpful, at least clinically. In 2018, we saw the first second generation clocks. And the second generation clocks took a step forward because instead of measuring against chronological age, they started measuring against blood biomarkers. So the first one that came out was pheno age, and that measured against 9 blood biomarkers. And Peter also mentions this one in his article. And pheno age did a better job at estimating your biological age because it was looking at these 9 biomarkers. These are things like CRP, and I think it was like liver enzymes and creatine or kidney function, something like that. And they looked at about 500 different CPG sites, or these sites where you get methylated. Another similar clock that Peter doesn't actually mention, that's actually probably more accurate, at least for mortality, is DNAm Age, which used about 1,000 CPG sites. And that one was trained towards when people die. So these were slightly better performers when estimating mortality, and got us up to about 2018. And that's kind of where Peter's article stops. He doesn't really talk about any third generation, or what I'm going to call fourth generation clocks, which have been coming out more recently. So let's mention a couple of those. So a third generation clock, the Dunedin pace clock, is trained on longitudinal data. And this is going to be super important when we start talking about Peter's criticisms of epigenetics. But instead of training it on a single time point, they're actually training it on multiple years of data that they collected in about 1,000 New Zealanders. And they looked at 21 different biomarkers in these New Zealanders over the course of their early life and middle age. And then they monitored them through health outcomes. So some of them developed disease, some of them died. So they were able to look at the epigenetic changes in those people that ended up dying or that ended up having disease. And this longitudinality, in this case, means the data was collected over time in that study, as opposed to just a single time point, like we saw with all the early clocks. So this is really important and extremely helpful for trying to estimate how accurate these clocks are for predicting disease and mortality, which is what you and I care about, as opposed to just predicting an age, which is not necessarily that helpful. And then most recently, the newest generation clock, which I'm not sure if I can call it the fourth generation clock or not, but I guess I'm going to, just because we've already gone through 1, 2, and 3, but a clock called DNAm Age. This was just published, and
like the 3.5 clock, maybe.
Yeah, maybe 3.1. I don't know,
7.
something like that. But it's almost like I think it needs a different generation, because it's a totally different style of clock. So this one's interesting because they took a multi-omic approach, as opposed to just looking at an epigenome and phenotypic data, like, for example, the patient's blood pressure or VO2 max or their blood biomarkers. They took a multi-omic approach. So they started with sort of a pheno age style, where they just used 19 blood biomarkers and created a clock that would perform better than pheno age on these 19 blood biomarkers. Remember, pheno age used 9. So now we've got 19. But then, to make it even more accurate, they actually looked at multi-omics. So what they did was they took 5,000 people and they looked at thousands of different multi-omic markers. So when I say multi-omics, I mean things like phenotypic data. So, blood pressure, height, weight, VO2 max, things like that. I mean, also metablymics. So that's going to include hormones and neurotransmitters, and protiomics, which includes the proteins that the cells actually produce. So the things that get transcribed by the DNA into actual proteins. So now, as opposed to just looking at just epigenetics, we're looking at like all of these different measures, like thousands of different measures of aging. And what they found is pretty remarkable. And we'll talk about this more. But I think this is the direction that these genetic clocks are going, and it's really impressive to see how much further they've come in terms of predicting disease and predicting mortality than from the things that Peter mentions in the study, which was mostly studies revolving around the Horvath clock, which was 2013, and the pheno age clock, which was 2018. So maybe we can go into the specific points, Matt, at this point.
Yeah, and I think, I mean, to be fair to Peter again, I think it's a good review of the literature up until this point,
Mhm.
until again several months ago or the last year or so. And the paper itself, just to be fair here as well, is not actually published yet. It's a preprint, and it's a preprint that came out, I think, October 24th, like less than a week before he published this. And we had heard about it. Like there's some YouTube videos and there's kind of some chatter about this. And for the last month or so, we'd been digging really deep and got really excited about this. So this is just something that's not on the radar of most people. And we're going to link to the preprint. It's called DNAm Age, an integrative multi-omics approach to quantify biologic age with electronic medical records. And we've reached out to the senior author, Dr. Jessica Lasky-Sue, to both have her like respond point by point to Peter's points, which are great points. They're points that people we've been trying to solve for a while, but I think they've solved for them. And we're also going to have her on the podcast to go really deep on the science, because even as you explained all of that you were explaining, Mike, I worried people got a little bit of lost in it already because it's complex,
Super
it's
complicated.
complicated
Yep.
science. So we're just going to cover a few of the things that Peter talked about and where we think some extra points could be made, but we'll go really deep with Dr. Lasky-Sue later on this, a much longer and in-depth podcast about science if you want to hear the real expert in this talk about it. But this is a study that just completely changed our minds, and we're using this for our patients. And maybe at the end I'll kind of explain. Well, let me just explain now a little bit my thinking on it, and then we'll go to these points, just a 60-second overview. I also have just not been excited in the past about biologic age testing, because if someone's 40 years old chronologically, I don't really care if biologically they're 36 or they're 44. My goal is going to be to optimize them. I really want to do tests that help me change management, that help me optimize someone, to help me reduce their age. We know aging is critically important. Like Peter would agree with this, that reducing someone's biologic age or slowing their aging down is going to be, it's the biggest risk factor for pretty much all chronic diseases. Aging is, it's more than obesity or all these other things that we think of are critically important. So it's really important. It's just, can we do something with the data when we get it? Is it reliable enough? And he makes all these points. We believe personally that now we can with these new tests, the Dunedin pace test and the omic age test. And so we'll talk a little bit about that. But to get into Peter's points, one of the main points that he made, the first one was the lack of longitudinal data. So the Horvath clock and other similar biological clocks, they were developed using healthy tissue samples from individual data sets without longitudinal data. And so this limitation means there's no way to differentiate the epigenetics of individuals with varying lifespans and health outcomes. So do you want to answer that point with regards to the newer clocks
Yeah.
and just kind of Dunedin pace and omic age, Mike?
Totally. This is a great point, and frankly, a big reason why I wasn't that excited about, just like you, Matt, I wasn't that excited about epigenetic age or biological age up until recently, because who cares what somebody's chronological age is, or how accurate epigenetics are at estimating chronological age. But to Peter's point, longitudinal data is necessary. It is necessary because we want to be able to use the data that we collect from these tests to understand how likely somebody is to contract a disease or to die. That's really the main point. Clinically, that's gonna help us the most, right? And the good news is we actually do have that. There are longitudinal studies out there. I mentioned, when I was going over the history a little bit, that the Dunedin pace model relies on multiple biomarkers, and those were measured at different points in the participants' lives. So those biomarkers encompass various aspects of physiological functioning. They were used to quantify the rate of aging among those study subjects. So they use things like lipid markers, CRP, liver enzymes, metabolic markers, kidney function. And that allowed them to track over time how the epigenome changed as those biomarkers changed. And what that really gives you is a phenotypic aging measure. So instead of just focusing on chronological age, you're now incorporating various phenotypic measures of aging, which means we understand how the epigenome changes based on these different blood samples, right? So if your CRP goes up, then we understand how your epigenome changed in response to that CRP going up. And we know that these blood markers are correlates of disease. I mean, these are the things that clinicians are using right now to determine whether you're likely to have cardiovascular disease, or whether you're going to develop cancer, or whether, there's evidence of inflammation in your body or insulin resistance. So all we're doing is sort of backtracking that to an epigenetic signature that we can then measure, right? Because your DNA, the way your DNA is packaged, changes based on how you're living your life, whether you've got inflammation, whether you have risk of cardiovascular disease. So this longitudinal data and understanding how these things change, and then understanding whether these people actually contracted disease or not, is what we can then use to help inform the model and get a more accurate model to understand the risk of disease. So, for example, the DNAm pace is represented as, instead of giving you an age, it gives you a rate of aging. So 1.0 is baseline. If your pace of aging is 1.2, now you're aging at basically 1.2 years for every chronological year. So, if I was now 40 and my pace is 1.2, then after the next year, my chronological age or my biological age would be 41.2 instead of 41, right? So that's how the pace is represented. And what we've seen is you can use that data and understand people's hazard ratios for mortality, for cardiovascular disease, for stroke, for TIA. And what we see is for every 0 or 0.2 increase of your pace, you see a hazard ratio for mortality of 1.64. So that's 64% increased risk of mortality just by seeing your pace change from 1 to 1.2. For cardiovascular disease, it's 1.39, which is basically a 40% increased risk of cardiovascular disease after seeing that pace change from 1.0 to 1.2. So, this can be really helpful when we're clinically trying to understand exactly what to do with this data, right? Like if I see generally that your pace is high, then I know that your risk of mortality is high. I know that your cardiovascular disease risk is high. I know that your risk of TIA or stroke is high. So we do have longitudinal data. It's presented in the DNAm pace model. It's also presented in the omic model, which I mentioned earlier. Omic is obviously the new kid on the block, so we don't have as much data to show right now that it's highly accurate, although the study is being released soon. So there is some information out there that's super useful, and that shows us longitudinal data.
Yeah, and the pace. I mean, when I learned about the Dunedin pace, which again Peter doesn't talk about in the article, I am now running that on myself like every couple weeks. I get excited because I saw things like they looked at pregnancy, for example, and saw that your pace score goes up. You got a kind of physiologic stressor there, and then it comes back down after pregnancy. So that tells you pregnancy is doing something physiologically. It's important. Same thing if you have a hip surgery, get a car accident, get COVID, any of these physiologic stressors make that pace go up. And so, it comes back down when you're over those. So I'm using this for myself. Like I took some senolytics that someone has sent me, and I'm repeating the pace test to see if it made a difference. They've looked at and kind of how long do you have to do an intervention to get a change? Well, they looked at it. There's a study of twins. I think it was 21 pairs of twins, and they fed them different diets, omnivore versus vegetarian diet, and looked at the effect. And you can see effect after 4 to 8 weeks in retesting on pace of aging. So I think we can actually follow interventions specifically and see how they're affecting you. I mean, people all the time ask us about, should we get stem cells? Well, I don't know. The data is not great, but even if the data show that stem cells are good, it shows that in a population. Well, I want to know, is it good for that person? So what I'm interested in doing now is getting a pace test, having someone, sure, if they want to do IV stem cells, go for it. And then we'll remeasure this again in 4 to 8 weeks and see if there's a change. So it's really interesting. And that's what I was saying earlier. I like tests where I can actually do an intervention and then see how it changes, have an objective measure. And I think the Dunedin pace gives us that.
And it's more accurate too. If you look at the Horvath clock, I mean, it had a 2% increased risk of mortality for the same variance, as opposed to the Dunedin pace, which had that 64% increased risk of mortality. So these clocks are getting a lot better. So sure, if we look at the old clocks, which is mostly what Peter's article was doing, then it's going to look crappy. But the stuff that's come out recently, since 2022, when the pace model really came out, is amazing, and I think, at least for me, clinically useful in my patient population.
Yeah, it's apples and oranges. And Peter's talking about apples, and we're talking about oranges. So I think that's the point here,
Yep.
and we'd love to get his thoughts on oranges at some point. One of the second points he makes is there's inadequate evidence linking biologic age to lifespan. He says there's currently insufficient evidence to support the assumption that a younger biological age correlates with a longer life. While cancerous tissues may show accelerated epigenetic aging, it's unclear if a younger biologic age translates into extended longevity. So you want to say what the oranges show on that instead of the apples
Yeah,
that Peter's talking about?
there's a few different responses to this one. So, I think we can definitely infer a link between biological age and lifespan, and there's some data to back that up. So there's studies showing a correlation with lifespan, and we've done this for multiple different clocks now. The two I'm going to mention are DNAm Age, which Peter didn't mention too much. This one was actually trained against mortality, and the hazard ratio for all-cause mortality for DNAm Age for every 1 year of age acceleration was 1.17, which is 17%, right? So 17% more likely to die if your biological age is 1 year above your chronological age. Omic Age, which is the study we mentioned that just came out or is just coming out, has an all-cause mortality hazard ratio of 1.22, so a 22% increased risk of dying for every 1 year of age acceleration. So that means basically, and also if you look at that Omic Age data, it can predict the risk of death in 10 years with a 92% accuracy, which is pretty impressive and way better than chronological age, which Peter inferred is a better predictor of mortality because chronological age only gives you a 70% accuracy of risk of death in 10 years. So certainly helpful. There's also longitudinal data, which we mentioned already with the DNAm study, knowing when people are dying or developing disease really improves the quality of these clocks because we're not just looking at a single time point, we're actually following them out to see if they died or developed disease. There's also research on age-related diseases. So studies have shown that accelerated biological aging, as measured by these epigenetic clocks, is associated with higher risks of age-related diseases like cardiovascular disease, Alzheimer's disease, stroke, and TIA, things like that. And that's obviously critical for determining lifespan. I mean, we know that lifespan is dependent on how early you contract diseases. Peter even mentions that in his article. So, for example, a 10-year variance in biological age and chronological age is associated with a hazard ratio of 1.9 for cardiovascular disease. So if, for example, I am 40 years old, but my biological age says that I'm 49, I have a 90% increased likelihood for developing cardiovascular disease. And that's really helpful. Like when we look at the large population studies, a hazard ratio of 1.9 for developing any disease process is pretty unheard of. I mean, like the polygenomic risk scores that we're using at Wild Health for cardiovascular disease gives us a hazard ratio of, I think, around like 1.35. So 35% increased risk for cardiovascular disease over the course of a lifetime. So these numbers are big. The 90% increase is quite large. Also looking at not just age-related diseases, but also looking at functional markers of age. So, as everyone knows, things like functional expiratory volume, grip strength, VO2 max are highly correlated with longevity. And we've seen that these tests like Omic Age, for example, can give us a correlation of up to like 0.8 accuracy for things like FEV or functional expiratory volume. So we can actually estimate these phenotypic markers of people. Like we can estimate their VO2 max, we can estimate their grip strength or their functional expiratory volume, which obviously helps us determine whether they're at high likelihood of mortality, because these things are directly associated with mortality. And then finally, the last thing I'll mention, then I'll shut up for a minute, is the intervention studies. So these are things like calorie restriction, for example, exercise, metformin, performing interventions that we would expect to show a improvement in longevity and seeing if these epigenetic clocks are picking up on it. And this has been done most recently through calorie restriction. So there was a study called the Calorie Trial, which is a 2-year study, and they did a 11% calorie restriction on their patients. This was done at Columbia University, I believe. And they looked at all the different clocks. Omic age wasn't out at the time of this publication, but pace was, the DNAm pace was, and that was the only clock that actually showed a reduction in biological age with caloric restriction. And this infers to us that we're now getting better at actually estimating your likelihood of mortality with these clocks through things like the pace clock, for example, and these third generation clocks, because the first and second generation clocks showed no change whatsoever with caloric restriction. So that is just telling us that if we actually do an intervention that we expect to improve the longevity of a patient, we're now seeing that, yes, their biological age is coming down, which again, for me, correlates that these clocks are well correlated with lifespan likelihood of longevity.
Yeah, my favorite part about that answer was when I named the problem and you said, "We've solved that," like you and I had anything to do with it. So I like that. We'll take
I'm doing the proverbial we. This is like the medicine longevity space in general. I didn't do any of this, science, man. All I did was read these articles. but yeah, like the proverbial we has figured this out. Science has figured it out. We science it.
Yeah, that's awesome. Another one of his criticisms was there's inconsistency in predictive values. So the predictive value of a biologic clock, it can vary across different tissue types, indicating that factors like hormones, tissue turnover, and stem cell recruitment may influence DNA methylation age. So this has been solved for as well by us specifically, you and I, right, Mike?
Yeah, I figured this out yesterday. No,
you can talk about how I solved this problem.
This is a really good point. Like especially if you're concerned about age in a specific organ system. Like say for example, somebody comes to you and they've got an APO3 E4 and they've got increased risk of dementia. And you're really interested in brain age, right? You know, otherwise they're pretty healthy. All their blood biomarkers are pretty good. You don't really care too much about other stuff. How accurate is a blood test, which is basically how all these clocks are trained. They're all trained on white blood cells. How accurate is that at determining somebody's brain age? And previously we would say,
Mike, one second about that. I think it's an important point. You just mentioned all these are trained on blood tests. This is one of the, in the past, we've used different clocks, and a lot of the clocks are using saliva still. And just one kind of aside is I would say if someone commercially is using saliva, I don't think I would trust that test so much. Yeah. So I just, you bringing up that they're trained on blood, I think is important. Yeah. Thing. So sorry.
Yep. Interrupt you, but all the good ones.
Point. There's so many commercially out there that are like using saliva and like, what is this? Like, why are we doing this? But sorry, go ahead.
Yeah. Don't use a test that's using saliva. Like you should be using a blood test. And those tests are basically looking at white blood cells. They're using the white blood cells to test the epigenome. And the challenge is that traditionally the age of your organ systems can vary pretty wildly. Based on obviously disease, right? You know, if you're somebody who's going to develop dementia, then I would expect your brain to probably be aging at a different rate than other systems in your body, right? Especially if that's how your genetics and your epigenetics are made up. So traditionally, this has been a problem. We're starting to get a better understanding of how you can actually use the blood epigenetics to infer with certain systems. And the way we're doing that is looking at populations of, and we again, the way that smart people are doing this is they're looking at populations of people who have the disease process that we're interested in. So if you take a large, subgroup of people that you've got a biobank on or something, you pull out all those people with dementia, and then you look at how is their epigenome in their blood different than those people who don't have dementia, right? So we're actually looking at outcomes now. We're understanding those people who die, who have mortality. How is their epigenome different than those people who don't? And if we look at those specific systems, now we can actually start to create signatures using the epigenome for specific organ systems. So I know that the people who made Omic Age are actually coming out with a test called Systems Age, I believe, which is looking at actually giving you an age for each organ system itself using this very protocol. So this is something that, while still relatively true, is being solved for in the short term, hopefully.
Do you want to talk about any kind of deconvolution or anything like that solving for this as well, or just you want to save that for the deeper dive?
So actually, I was planning on talking about deconvolution with another one of Peter's comments around variability across cell types. I can do that right now.
Yeah, across cell types. Yeah.
Yeah. So
No, let me just skip to that, and you can
okay.
answer that question. So let me just phrase the issue for people. So Peter also talks about different causes for inaccuracy in the reporting. So methylation is affected by more than age. So factors like smoking and sleep deprivation, known to alter DNA methylation patterns, suggest that lifestyle behaviors significantly impact epigenetic aging. Accurately predicting mortality risk may require accounting for such behaviors. There's three parts to this. You want to answer that one first, or do you want me to read all three of
Just
these?
read all three. I'll just go through all three of them at once.
All right. The next thing is the biological and technical noise. So daily fluctuations in behaviors and technical limitations in measuring methylation levels introduce noise that can obscure the effects of geroprotective interventions or lifestyle changes. And then the third one is variability across cell types, which is what we were getting ready to talk about. Significant discrepancies in epigenetic age predictions between different cell types and tissues challenge the assumption that various tissues age at the same rate. And one thing before you answer, I'll say is all of these things are dense. So I think it's going to be important now as I'm like, we're going through this even, I'm like realizing that having that line by line answered by Dr. Jessica Lasky Sue and the authors of this paper is going to be important. So if you get lost at all in this talk that we're doing here, just listening to this audibly, we're going to, if you want to go deeper, if you don't care, great. If you do care, we're going to like annotate all of this and kind of line it out for you, but go ahead and audibly answer these three, and
Yeah.
hopefully somebody will get something.
I'm going to do my best to keep this simple because these are like probably the most complex parts of it. But let's take the variability across cell types because you mentioned the white blood cells and the immune deconvolution method, which I feel like you just saying those words, I just lost 50% of the audience. So the issue is that there's lots of different white blood cells, right? So you don't just have one type of white blood cell. There's these things called T cells, there's B cells, there's natural killer cells. There's all kinds of different white blood cells. There's like, I don't know, 15 different subtypes or something like that. And the issue is that each one of these cells changes. The percentage of those cells in your system change, right? I mean, this is how your immune system works. Like you get sick, you're going to have, a variation in the number of T cells versus B cells or the number of natural killer cells that come out. So as we go through daily life, there's this variability in the percentage of your white blood cells, the types that make up your total white blood cells. And if we're using white blood cells in general, all of these subtypes to measure your epigenetic age, as that percentage changes, if I'm getting a different age from different types, then now I'm getting a different age, right? So that's a major issue. And this has been realized as a big problem with epigenetic clocks since about 2019 or somewhere around there. Zhang published a paper that showed that you could actually affect somebody's age by like 9 years just by controlling for the types of white blood cells that are in the person's blood. So once we realized this, we realized, whoa, there's a big problem here. And this has been alluded to as a possible cause of some of the variation that we see in a lot of these older or basically in all of the clocks for that matter. So the Omic Age people published a study looking at basically taking the epigenetic signature of the white blood cells to figure out what's the percentage in circulation without actually having to do like a separate test to figure out how many white blood cells are in circulation, and then go back and correct for what the age is. So this variability that we see with white blood cells is in fact being fixed by this cell deconvolution method. So it's really just a matter of looking and figuring out how many different types of white blood cells do you have, and then how does that affect your overall age.
Awesome. Sorry, I fell asleep there for a second. Everybody else, wake up. We're almost done. We're bringing it home. I promise. The last thing we're going to cover before. Sorry, what are you going to say, Mike?
There's a couple more things. So there's two more points that he made in that whole section. Okay, let me hit those real quick. So there was
don't stop talking, because when you stop talking, I wake up because it gets quiet all of a sudden. So keep rolling.
I understand. There's the point that methylation is affected by more than age. And to this one, I don't really know how exactly to respond other than say, like, I think that's the point, right? Like, the point is that we're trying to figure out how your lifestyle, how your risk of disease affects your biological age. So I actually want that. I want the methylation test to be modified by the way you live your life, because that allows me to then take that number, that biological number, and understand, how are you doing compared to your chronological age? So for me, that's actually a bonus for these tests that, we can use something like the pace. Matt, you were saying that you're doing a pace like every month now. And I think that's kind of the idea here is that we make interventions, we check our pace again, see how they've changed. So maybe you want to start taking like some senolytic, for example. So, you do a pace before you start the senolytic. You try to keep the rest of your life relatively consistent. And then you do another pace in a month after taking that senolytic and see what happens. Did it work for you? I mean, this is potentially a way for us to measure how our interventions that we're trying to do for longevity are actually performing, which is obviously extremely important, because otherwise you're just guessing, right? And a lot of, as Peter's brought up, a lot of our blood biomarkers are really terrible at measuring, longevity and effect of these things. Like there's no way to measure whether NAD plus works. There's no way to really measure whether these senolytic cells work, other than something that you could do in a lab or a research department, So this PACE test, is potentially a way to go back and say, did this intervention that I am performing, fasting for 5 days, did that work? Did that help me? Am I now aging at a younger rate than I was previously? So that's super important. The other thing he mentioned was biological and technical noise. So this is a great point. The first study that came out, the Horvath clock, came out in 2013, we mentioned, had a huge variance in some of its samples, like up to like 30 or 50%. So imagine your true biological age is 60. That means that your sample could vary as much as 18 years based on, if you just did like a sample literally one after the other. The variance was huge with some of these early tests. Peter even mentioned that Japanese study that came out.
Making it not useful.
Yeah, not useful at all. Yeah. Peter mentioned that Japanese study that came out that showed, a giant variance with multiple different tests. And that study he mentioned was done using PhenoAge, and it was done using the version of PhenoAge that was before they came up with some statistical magic to improve the quality of all of these clocks. So in 2022, Morgan Levine released a paper basically talking about a computational solution for these. So basically a statistical trick to improve the quality of all these clocks. And it took the precision of these clocks and the accuracy, or just the precision, not the accuracy, down by almost a factor of 10. So instead of being like 30 to 50% variance, now most of them are less than 5% variance. And then using that same component analysis, the variance of omic age, for example, is now down to less than about 0.5%. So 0.5%, 99.5%. Precision is what we expect now across these clocks. So this is a true point that Peter made, but it's an old point, and it's a point that that has been fixed, not by me, but by super smart people that can pronounce these words even better than I can. Hopefully, I didn't lose anybody with that one, but it's basically just mathematical awesomeness that some people at the big institutions came up with.
Yeah, no, you definitely lost people. That's okay. The other point I'll make about, you mentioned the Japanese study. I think this is a perfect point in Peter's article. Like what he said is technically accurate. He's talking about this Japanese study where there are daily changes of between 5 and 6 years. Yes, that's true. But this is a study that used a 450K array, which was discontinued since 2018. So while it's true, it's not really pertinent to the question that we're trying to answer of, is this a useful test or not? Again, we're talking about apples and oranges. He's talking about apples and we're talking about oranges.
Yep.
So the last point, and not to get into all the different arrays and things and make all those points, because I think Dr. Jessica Lasky-Sue could make those better. The last big point we want to talk about is he mentions there's so limited insight into lifespan and geroprotective interventions. So current biological clocks do not provide actionable insights into expected lifespan or the efficacy of geroprotective interventions, serving more as a research tool than a practical guide for individual health decisions. I mean, one thing I'll just say about that in general is I am using this. Like he's saying, it's just for research tools now, not a practical guide for individual health decisions. So when I read the studies, and I got really excited about the DNAm pace and omic age, I am using it for myself as a practical guide for individual health decisions, like I just mentioned. The variation you kind of mentioned earlier, and like it could be 5 or 6 years off. And I had the same issue when we first started using these biological clocks. We used a lot of different ones over the last 4 to 5 years. And we would see this. You could send the same sample, the same person, and it's off by a few years. That's not the case with the Dunedin pace and the omic age. So the Dunedin pace, the variability, the ICC for this, which is the technical term, it varies, same sample, same person, about less than 1%, like 0.05%. So that's why I feel okay doing this like once a month, because if I see a difference, I believe it's actually a difference and not just a statistical error. So while what he says is, I believe that too, and I saw that in the past, I don't think it's true with these clocks that we're using, and that's why we wanted to talk about.
Sorry, so yeah, so I mean, also with regard to that, Matt, I mean, you mentioned that it's more accurate, but also with omic age, we're actually getting some estimations of these biomarkers. So because it's a multi-omic approach, you're actually starting to understand what we expect some of these biomarkers to be, and by doing that, we can infer what's actually causing the speed of aging. So rather than just getting a number back, now we're seeing, what are those biomarkers that are off, that are likely the biggest cause of aging. So we can rank order, the different systems that are causing the aging, and in some cases even like the proteomics, the metabolomics that are most likely causing the aging to be at a faster rate than we would expect. So with omics, we're actually getting these specific interventions that may have the greatest impact on aging, which is a huge step forward for this whole area. I mean, this is something that we haven't been able to do with any prior test. So with these 4th generation tests now, we're looking at the opportunity to start to be able to give patients specific interventions to improve their rate of aging.
Yeah, and I'll give an example just to kind of bring that point home. And technically, what I was talking about is not the accuracy. I was talking about the precision of these tests. And I think we've already made kind of the argument that the accuracy is much better with these tests, but the precision and the repeatability needs to be there as well, which it is, which allows us to retest. But for me specifically, again, we got excited about this. I started doing it for myself, and when I dug into the test. You're talking about, and we haven't talked about this, but these EBPs are epigenetic biomarker proxies. We haven't talked about that much, but they can actually estimate, okay, what is your DNA methylated proxy of CRP or hemoglobin A1C or these things, to actually see potentially what is causing the aging to be faster or slower. And they don't match up perfectly with like your lab core value of that, but they give you really nice directional information to potentially what you could work on. So for me, we dug into my test. I had a really good pace score. I work really hard at this. I do a lot of things right. The one thing that popped out that seemed to have like the biggest potential magnitude of effect for me was if I had more carotenoids. Like I would have never figured that out. So eating more carrots, like yellow carrots, or just taking a carotenoid supplement, I would have never figured that out. That's not like a lab test that I order from LabCorp. I follow my A1C and my CRP and my triglycerides and my ApoB and all of these other things. I don't follow my like carotenoids, like what level. And so I found that. And so I ordered a supplement. That's one of the things I've changed as I'm like continuing to see how that changes over time. So that's the kind of directionality. So it's not only can we do these N of 1 experiments to see, does the stem cells work for us or not, for example, but also we get some clues as to what we should try first instead of randomly trying a lot of different things. So that's why we're so excited. That's why we're doing it for ourselves. I think there's a couple things that I know as we try to start to bring this home. One is that we're not the experts, Mike and I. So I know for a fact that we probably got some technical things wrong in this podcast. So I want to say, if you've listened to this and you are one of those world experts, like forgive us and be patient with us as we get the world experts on. Like we're going to get Dr. Laskusu on here to really talk about this. The other thing I know is that we're pumped about this testing. Like I found a video, actually we'll link to this, of Dr. Laskusu talking about this, giving a presentation on it. I've watched that. It's an hour and 18 minutes. It's an hour and 18 minutes long. I've watched it 3 times now, because it's dense, but it's also really exciting and interesting. And this is why we're ordering this. We felt like we had to talk about this too, because a couple of weeks ago, we made the decision to get this test on all of our new patients when they sign up for Wild Health. We're not sure if we're going to do that forever, but we want to do a trial. Like anyone that signs up in 2023, the rest of the year, we've decided to do a trial and include it for free. We're not increasing the price at all. I think if you just order this, test. It's like a $500 test online. We're just including it in everybody who signs up because we want to start collecting a lot of data on it. We want to use it as a piece of the puzzle to help guide interventions. We're still getting genomics. We're still getting blood work. We're still talking to patients, getting medical history, family history, all of those things. But when I started realizing that I was going to do this on myself every 2 to 4 weeks, I felt guilty. Like, why am I not doing this on our patients as well? If I think it's that useful for me, then we should be doing it for patients as well. So we're going to follow up with a deeper dive. We reached out to the authors of the paper. We're going to do that. We just want to get this quick response out there. And I also want to just end by saying, like, we mean no disrespect to Dr. Peter Attia. That would be foolish. I mean, everybody respects Peter. Mike, you may not have known this, but Peter actually doesn't have a shadow. Like, even the darkness retreats out of respect for his knowledge on health and fitness. So absolutely. And actually that is I think everyone actually does know. If you're ever around him, it's creepy. Like, there's no shadow just because the like retreats out of respect. So not Peter's way smarter than us. Like, sorry if we've offended anybody there. We just want to add to the conversation, and we promise to come back with some real experts and go deeper on this if anybody's interested.
Thanks so much for listening to the Wild Health Podcast. If you want more daily health education, be sure to follow us on Instagram, which is filled with health optimization how-tos, grocery shopping lists, guided breathwork posts, myth debunking, and so much more. You can find us at Wild Health MD on Instagram.